Good morning, everyone. We're with Team 7, and we're going to present a proposal on a user-settable G-switch. I'm Sean Van Haren. I'm the manager for the team.
I'm Tom Lauder, and I am the documentation prep.
I'm Frank Doherty, I'm the webmaster.
David Eaton, I'm the presentation prep.
Xiao Xu, I'm the lab planner.
And our facilitator was Dr. Dean Aslam with our sponsor, Greg Horschel at Instrumented Sensor Technology Incorporated. What we're going to talk about today, I'm going to start us out with a background behind IST, the problem in general and the requirements that our sponsor gave us, the solution that we have for it, and then we're going to run down from there basically everything else that we're going to use in our solution, as well as the product choices, and then we're going to finish with our risk analysis and budget. Background behind Instrumented Sensor Technology. They're a group or a company that started in 1987, and based out of Okemos, Michigan. They have 20 engineers and technicians currently working for them, and they're most well known by their 3-axis accelerometer data loggers, but they also have humidity and temperature sensor loggers as well. The 3-axis accelerometers are used mainly in crash sensor reconstruction, and they are also used in their shipping crates, and they have a bunch of shock timers as well that they use mainly for shipping. Keynotes that companies that they've worked for, they've worked with NASA in their shipping of their reusable solid rocket fuel and their shipping crates, as well as the armed forces and shipping water-based radar defense and their shipping of that as well with their shock timers. They've also worked with Mythbusters and testing the myth of high fall into a body of water, breaking the surface tension before you hit the water. By the way, the myth is busted. A general problem that will arise in anything that involves in vibration or shock, there will be the biggest concerns in heavy machinery and industry, as well as like power plants. So if a generator or motor starts to oscillate out of control, it could cause damage that could back up production for weeks, if not months, and just cause a lot of loss of money for the company. Also, outside damage of like destructive weather and just nature earthquakes that could cause the machines to oscillate out of control and damage them. Other things that we won't be going into as much that the company deals with a lot is the shipping and the vehicles and just large areas of vibration and shock. And now, take it over to Tom, and we'll talk about the problem requirements.
Hey guys, I'm Tom, and here are some of the project requirements given to us by Greg at IST. As you can see, we need to operate from DC to 100 Hertz. We need to be able to set the G-force levels using a dip switch. We need to set the levels that we're going to detect on our device. And we also have to be able to choose between RMS and peak detection modes. We have to work with wall power and a high amperage. One of the uses for our device could be like hooked up to a washing machine. And that's quite a bit of current going through about 1 kilowatt. So we need to be able to use a relay. We need to be able to use a relay that can handle a lot of power. We have a couple options for power too. We either need to power this thing with a battery for 6 months or work off of wall power, in which case we'll have a backup battery in case it's disconnected. And this thing can be no larger than 12 cubic inches, and there needs to be a screw terminal strip exterior to it that we can hook up the power leads to. As you can see here, here's our table of G-level requirements. These are the settings that we'll have to be able to choose with the dip switch. Peak mode goes from 1/4 G to 6 Gs, and then RMS mode 0.0625 Gs to 2 Gs. And so our proposed solution for our problem is the user-settable G-switch. And it's going to be a small, self-contained device that can be mounted on the machine or device or building or whatever we're supposed to be monitoring. And it's basically just going to trip a relay that will be necessary for either cutting power to the machine it's attached to, or it'll start a control program that'll do like a soft shutdown or something like that. And our device will also visually indicate when it's tripped by blinking LEDs. There'll be a blinking green LED for untrip mode and blinking red LED for trip mode. Here's our circuit structure for our device. As you can see over here, we have our accelerometer, which has a lot of internal functions already built into it. Sean will talk about all that later. That sends signals to the microcontroller, which then controls everything else. It basically takes the level from the accelerometer and it compares it with the level that we set with the dip switch. And if the accelerometer's level exceeds the dip switch setting, then it'll go from blinking green LED to blinking a red LED, and then it will also activate our output relays. And so now I'm going to hand it off to Xiao, who's going to talk about our dip switch.
Morning class, as Sean said, I'm Xiao, and I'm going to be talking about how we utilize the dip switch and interface it with our microcontroller. So as you can see that we have we're using a 4 single pole, single throw switch, which results in 4 bits. As you can see that the first bit is just telling us what detection mode we're going to be using. So if it's a 0, we're going to be in peak detection mode. If it's a 1, we're going to MMS. And the next 3 digits pretty much determine what the trip levels are. So for example, if it's 0011, we're going to be doing 1G at peak detection mode. And one issue we had when we were doing this is because we're using 4 bits, and that will leave up 4 extra settings that just wasn't assigned. So we just assigned extra, 0.75G, 1.5G to the unused dip settings, so to avoid confusion with the customer and to make programming a little easier than us, so that the customer can have better resolution in their trip setting levels. So the accelerometer that we use is the BMA 250 by Bosch. Well, first of all, it is made by Bosch, which is a requirement because our sponsor actually has a deal with Bosch, and you can get both of these at a discounted price. And it's an XYZ triaxle, which is another requirement. And the desired output, this thing ranges from plus minus 2G all the way up to plus minus 16G, which is settable by the user. So it fits perfectly into our plus minus 6G requirement. It also has a digital output, which makes the programming a lot easier for us. It's got a user settable 1 to 8 hertz all the way to 1 kilohertz bandwidth with a built-in filter. So we're going to be running this from DC to 100 hertz, so this is definitely within our range. It's got a very nice resolution at 3.91 millig's, and it's also very, very small at 2 by 2 millimeters and like less than 1 millimeter in height, which is what we need. One of the requirements that Tom said is that we need to have a lot of battery life. So this actually runs at 0.5 microamps in suspended mode and 7 in low power mode, which is exactly what we need. And lastly, it's very shock. It has high shock survivability because you don't want this to break when we're actually measuring the acceleration. The microcontroller we decided to use is the MSP 430 by TI. Many of you probably used this before. It's very low cost, very easy to use, as C is a programmable language that it supports. It has a very large, there's a very large community online, both by the users, their blogs, or even the TI that supports this device, so we can get a lot of the sample codes from just Googling, I guess, and then modifying to meet our functions. And it does everything we need. We can code it to do RMS calculation, peak detection, and it's got a 32 kilohertz crystal clock built in. And to meet our 100 hertz bandwidth, we'll probably need like a 500 hertz Nyquist frequency, so that meets it that's way past what we need, so that's perfect. And once again, it's low power, and it consumes 220 microamps at 1 megahertz. We're probably gonna be running the clock at like maybe 500, so that's pretty good. And we're gonna be we're gonna be developing this with the LaunchMad. Once again, it's very low cost, and it's got a USB connection and dip sockets, so we can remove, add, remove the microprocessors at ease for very easy prototyping. And now I'm gonna pass it on to DJ.
Hi everybody, my name is David Eaton. I'm going to talk about the code a little bit, the code flow. What we want to do for with the C programming is first we want to start it off when we want to close relay 1, close relay 2. Basically that's the startup of our motor. By closing that first relay, we're going to basically initialize the motor, the pump, and get it to start running. And then by opening the second relay, we're basically acknowledging that it's starting on. And the second step, we got to read from the accelerometer and from the dip switch and send that to our microprocessor. We basically want to read all of that, and this is where the chunk of all of the actual program is going to be. We need to check our accelerometer against our user settings. So basically, we have to make sure that our G level coming from our accelerometer is under the acceptable limit from the user in the dip switch. So over here is the loop in the situation that the accelerometer is under the limit. We're basically going to sit there and just blink the green LED, not do very much, not change anything, because right now it's acceptable. We're happy with where the G levels are at. But in the other situation where the microcontroller might trip, you first immediately got to open your relay 1, close your relay 2. By opening your relay 1, you are now turning off your motor, or making it basically shut down. We're trying to save the machinery so there's no more damage that gets affected by it. And then also by closing the second relay, you can basically hook up basically a horn or something along those lines to the second relay so that when this thing trips, you're telling somebody back in the control center that this thing did trip and something's wrong with it, you need to go out there and fix it. And then coming back down, we got another loop. We're basically blinking the red LED on our little device. It's going to sit there in that loop, and our sponsor made it pretty clear that he wanted a reset switch on this device so that when this thing trips, when these relays open and close, we want to make sure that nothing can happen to it. It's not going to go back to its original state before a user comes up there and manually presses the reset switch. So basically that's kind of the code that we're going to start doing when we start programming our microcontroller. A few issues that we still have to overcome is our relay choice. We haven't yet decided what we want to do on that. Right now we have the choice between a solid state or mechanical relay. And as you can tell right now, we're most likely going to go with the solid state relay because it has a much better advantage than the mechanical one. A few advantages of the solid state relay is that it has a low minimum latching current, which is a benefit of ours because our microprocessor doesn't output very much current. So it's important that it has a very low latching current so we can actually change the state from open to close. It's a very fast switching time and a longer lifespan, and it doesn't bounce. It's a very clean operation. That's all because there's actually no moving parts compared to the mechanical relay. It has a switch that moves back and forth. The solid state relay is just circuitry, so it lasts a lot longer. I think the lifespan says it's over 1 million to maybe 10 million switches, so that's quite more than the mechanical relay. It's also less affected by the environment. The mechanical relay can be affected or can affect machinery around it. And then finally, the last option, we can design our own onboard relay if we want to for our project. The problem with our relays right now is that they wanted 125 volts, 10 amps, which is over a kilowatt of power, which is quite a lot of power to send through this device. So these options become really large in size when you start doing large amps like that. So we want to meet our 12 cubic inches measurement, but these options are kind of messing that up because they're really big in size. The mechanical relay, however, has its benefits also. It has a better fail-safe mode. If we were to lose power or something was to happen to our microcontroller, we know the fail-safe mode that these mechanical relays will fail back to, so that's a benefit. That's very important in the power industry and mechanical industry. They're very cheap, very diverse, and very accessible. They're used a lot in the industry, so it's very easy to come by them. A lot of people sell them. Makes it a lot cheaper for us, which is a benefit. And then our risk analysis. The biggest thing that we need out of our project is it needs to be very durable and it's in hazardous conditions. Basically, it needs to be able to survive up to 6 Gs, just like the machinery. You know, if it can't handle that, then what's the point of buying our product? It's going to be in heat conditions. It's also going to be very dirty conditions, so it needs to be able to withstand both of those. We want low power consumption, as said before, because we want a 6-month battery life out of it if we use the battery. We basically just want it to draw as less current as possible. And finally, we need this to be as portable and easy to install and take apart as possible. We need this to be very easy for the user to do, and we want to make sure that anyone can be able to use this if they wanted to. And then I'll bring it over to Frank for the pros and cons and to wrap up the project.
Thank you, David. I'm Frank again, and here are some pros and cons. There aren't too many cons, fortunately, but our pros are it's low power consumption, and this is with the design that we've been choosing. It's pretty low cost. I'll go over that in the next slide for the budget, but it's very low cost. You can set it and forget it. It's easy to use. A person has a manual and just sets it up right at the beginning, and then you leave it for the use. It's a small design, portable, easy to put and like carry and install, I guess. The only problem is it does have to last for 6 months on batteries, so maybe one battery might not be enough, but we are working with ultra low power consumption devices, so it probably will be. And the situation is that it will need to withstand a lot of Gs, so it does have to be durable enough. But we will hopefully design for that. This is our budget. It's just over $100. The biggest cost is relay, and we haven't completely picked that yet, but we have picked the accelerometer and the boards, and this is for our final design, the PC board. But it's low cost, it should be feasible, it should be very competitive. So one last time, I'll do a conclusion. Our task that was given to us was to build a self-contained device that can open or close a relay with G-force limits that exceeds a certain settable limit. But with this, we are making the G-switch, which is displayed here in a block diagram. And it is driven by a microcontroller. The accelerometer measures the G-forces, which sends digital output to the microcontroller and compares it to the dip switch. And the dip switch has 8 peak values and 8 RMS values that the user can set. And that information is compared and sent to 2 relays, which are 125 volt, 10 amp solid state relays that we're probably going to choose. And that can turn off the machine if there's 2 LEDs again that can communicate with the user. If it's blinking red, it's been tripped. If it's blinking green, it hasn't been. And also a reset button so you can use it one more time or continuously after it's been tripped. And this is just a sort of ridiculous example of what it can save. But I guess, as you can watch, it would trip right as the brick enters the washing machine, because it senses the radical movements and would shut off the machine and not cause such a destructive force. But the technical roles are Shao and David are doing the software development. Tom is doing the circuit and PCB design. Me and Sean are leading the assembly and testing. Any questions? Thanks, guys.
Oh, we got a question.
How are you guys going to present your final design? Are you going to do anything with a washing machine or anything like that?
So, we did talk about that with our sponsor. So, it's not a bad idea. It'd be kind of hard to wheel a washing machine into the Union, but I think that'd be a good demonstration anyways. So no, we might actually do something more feasible. like honestly, really all you could do is just shake the thing and.
Well,
the
our,
light will
our
switch
sponsor
over.
actually has this handheld
Yeah.
measuring kind of testing machine that vibrates at a certain settable G level. So
Yeah.
what we can do is maybe set that on that portable thing and then, our sponsor's got a bunch of testing equipment, so I mean, it's definitely, so we can definitely work something out.
We have a lot of budget left.
Yeah.
Yeah, we have plenty of
Probably
money to
can
come
buy
up
a washing machine if that's,
with. We'll have enough money to come up with something exciting.
yeah.
Yeah.
I was wondering if you looked into how noise can affect the system, because I've always thought about this. If you have a accelerometer controlling your airbag in your car, and all of a sudden the accelerometer has noise, is your airbag going to go off? I mean, is there any precautions you can take to prevent erratic triggering?
The use of filters, right?
Well,
Yes.
right now, we're trying to pick a relay that doesn't have a lot of, a lot of, again, field to the switches, so that's one thing we're trying to
That's
do.
good, yeah.
But
The use of the low pass filters and the accelerometer would be good for that.
Okay.
Like Sean was saying, I think there's 8 selectable low pass settings, so if 100 hertz isn't pushing it, we could even lower the limit. But, yeah.
You said the accelerometer was ±2 to ±16.
yeah.
Does that include the smaller values?
Yeah, there's a bunch of settings in between that you can
Okay.
choose, like +4, 6, 8, 16.
What about the smaller values? You have to go down to what?
Five.
So it means like the top
160?
value is +2.
Oh.
plus
Yeah,
16,
so it's-
And then it does the range underneath it.
Yeah.
Oh, okay.
Any other questions? All right. Thanks, guys.